So we are going to start our first chapter from the book, which is chapter 3. So we'll start our discussion from here. So, and then we'll go back and forth. So, and then as you can follow from the weekly schedule. So now, this is actually the beginning of the digital circuit. So in the digital circuit, just like the components that you use in the electric circuit, like the resistors, the batteries, and the different kind of loads, we have something a little bit different. So we use a lot of logic gates. These gates generate different kind of logic. Now remember, no matter what logic you have, is always will be defined by the binary numbers, because digital circuits only run on the logics. Okay, even if the logic means voltages, because at any point in the digital circuit you might have voltage 5 or you might have voltage 0. Okay, but the voltage 5 means the logic 1, which is also you can compare with binary 1, and the voltage 0 means logic 0, which also means binary 0. Okay, but from now on, from this class on, in any part of the digital circuit, we'll never probably talk about the voltages. We'll always talk about the logic. Okay, because as I said, digital circuit is run by the logic. Okay, and you can always assume, if we just say, oh, the voltage, if the logic is 1, that means you know that the voltage is 5. We don't mention it every time, and sometimes instead of just 1 and 0, we sometimes just say high and low. That's exactly the same thing. High means 1, low means 0. Okay, now, so all these logic gates actually comes as an IC. Once we start the lab, you'll be able to see those ICs. I'll probably show you a little bit of IC numbers and things today, but you will see those ICs better, and then you'll exactly know how these logic gates are used. But in the real circuit, we just write these logic gates as just using some symbols. Remember, think about the electric circuit class. You have the real register, right? But think about how you draw the register in the circuit, right? That's not quite same, right? But similarly, in the digital circuit, we have the symbols for different gates. But the real gates are just like some ICs. For an example, the very first gate here we have is called inverter, or sometimes we call it NOT gate. Okay. Now look at the symbol here. See, it's like, so this is like any gate, you will actually have some input lines. There might be 1 line, there might be 2 lines, in some cases 3 lines. So for an example, this is the input line of the gate, and all the gates will give you a single output, which is most of the time we write as an X. Okay. Now here, see the input line, and this is like a triangle followed by a small bubble, right? So this is the symbol for the inverter. And just by the name of the inverter, you can guess that what exactly it does. It actually inverts the logic. That means if you input 0, it gives you 1. If you input 1, it gives you 0. Very simple. Okay? Because as I said, we always talk about the logic here. So for every digital, I'm saying in the digital circuit, for every logic gate, the behavior of the logic gate we define by a table, which is called truth table. So for an example, this is at the bottom, this is the truth table of the gate. This truth table actually will tell how exactly the gate behaves for different inputs. Like, given input, what will be the output? You know what I'm saying? So as you can see, there is only one input line. So what you can give the input? Either 0 or 1, right? Think about the digital circuit. It will be always 1 and 0, nothing else. So your input can be 0. If it is 0 or low, the output will be what? High or 1, right? Because it just flips the logic, nothing else. And if the input is high, the output will be low. And that's very simple, right? So this is the truth table for inverter. In addition to the gate, symbol, truth table, there is something which is also very unique in the digital circuit, that every logic gate and every circuit, in fact, can be represented by expression, like by math expression. See, for an example, see, you have seen a lot of math expression, right? So in fact, every gate, even for every circuit, no matter how big the circuit is, you can write a single expression for the circuit, and then that actually will tell how the circuit behaves. You can even read the expression, and then you can draw the circuit at some point. Okay? We are just beginning, so a lot of things you probably don't know at this point. I'm just giving you some hints. Okay, now, so for every gate, we'll actually try to write an expression which is pretty unique to this gate, which actually will tell how the gate works. For an example, here is the expression for this gate. Now, X is the output, right? Which is the inversion of the input. Now, you see here, A is the input, right? And on top of A, there is a bar. Do you see there? This bar is also called complement. This actually flips the logic, okay? Meaning whatever the A, X will be the reverse logic. Like if A is 0, if X will be 1. If A is 1, X will be 0. Now, as you can guess, that bar is hard to write in many places like pause. You can't write bar on top of A, right? So in several literature, instead of bar, we use something like prime. This is a prime. You see this one? Just right after A, you see there is a small prime. So instead of A bar, we just write A prime. That's exactly the same thing, okay? So in our class, in pause, we'll be just writing A prime. That actually means A bar, okay? That's the expression for the inverter. So there will be expression for every gate. So this class will actually talk about the very basic and popular gates that we will use for this class and for most of the digital circuits. Now, in digital circuit, there are only 3 gates which are called the basic gates. The reason is, these are the gates you can use to build every single digital circuit of the world. Even you can build a computer with these 3 gates, okay? And this is the first basic gate. We'll talk about the other 2 also, and then we'll talk about some more gates. Now, to explain the gate, I just randomly have drawn a waveform, okay? Now, in the electric circuit class, I'm sure you have seen different kind of waveforms. You might have seen like sinusoidal waveforms, triangular waveforms. But in the digital circuit, it's a little bit easier because you will be always get like pulses. Because as I said, digital circuit, it will be always zeros and ones, right? So this pulse means what? So you have 0 up to this point, and then it becomes 1 here, right? And you have 1 up to this point, and then again is 0. You have 0 up to this point, and then again 1, right? So, you know, it will be just always 1 and 0, okay? Now, you might be wondering, how did I get this A? Actually, I have just drawn it randomly, okay? So I just wanted to show you, given this A, what will be the X? X is what? Output, right? So, as you can guess, X will be just flip, right? See, it's actually flip, right? Whenever A was 0, X is 1. Whenever A is 1, X is 0. Pretty simple, okay? I just wanted to show you. So this is an example. So remember, in the ones complement, we have to flip all the bits, right? So you can use like 8 inverter to flip all the gates, right? So for an example, if these are the input, you can flip all the gates, right? Just by this. So now you can probably connect that why we do the subtraction in a completely different manner, because as I said, the subtraction we learned, that is a subtraction which is pretty much something is followed by every digital circuit. Because in the digital circuit, we have logic gates, and we have to do all those operations using the logic gates. So you don't have to understand the example at this point. I just put the example just for curiosity. Now, this is our second basic gate. This is called AND gate, okay? Now, this gate has 2 inputs. Actually, most of the gates we'll be talking about today is actually has more. All of the gates have two inputs except the inverter, okay? Now, this has 2 input, A and B, and always the output is one output, which is X. Do you see the symbol? These symbols are crucial because at some point you actually have to remember this symbol so that you can just see the circuit and you will know exactly what gate it is and what should be the property of the gate, because you can tell from there. Now, the AND gate gives you a high when both of the inputs are high. Otherwise, it always gives you a low, and that's the property of the AND gate. Now, let's try to write the truth table. Now, remember, there are 2 inputs, right? So there will be actually 4 combinations. What will be the combination? 0, 0, 0, 1, 1, 0, and 1, 1, right? That's the best, that's the max combination you can write using 2 input, right? For every combination, you will get an output. So remember, what is the property of AND gate? It gives you a high when both of the inputs are high, right? Otherwise, it gives you low. Again, what is high? High means 1. What is low? 0, right? So for 0, 0, output will be 0, right? For 0, 1, it will be still 0. For 0, 0, 1, 0, it will be still 0. It will be 1 when both of the inputs are 1, right? That's exactly what the AND gate means, that it will give you high when both of the inputs are high. That's exactly how this gate behaves. Now again, just like any other gate, there is an expression for this gate. The expression actually is x equals to a dot b. Now this dot means AND. Okay, this is called AND operation, which actually behaves like just AND gate. But just like the math, remember in the math we don't write the dot, right? When we do the multiplication we have dot, right? But we don't write the dot. Similarly in the binary operation we also don't write a dot. So instead of just writing a dot b, we just write x equals to ab. But whenever we write this, we know that there is a dot. This dot is the AND operation. It is also called binary multiplication because it looks like multiplication, right? See, think about the dot in math. You know, in the regular math, we use the dot for multiplication, right? It's pretty similar. But again, it's not exactly the same like math because you are actually doing the AND operation instead of doing the traditional multiplication. You are actually doing the binary multiplication. Now to understand the gate, I actually randomly gave you two different waveforms. The reason we have two waveforms because we have two inputs, right? And we want to show you how the output will look like based on these waveforms. I just draw the waveforms randomly. I have drawn it, okay? Now remember what AND gate does. It gives you a high when both of those are high, right? So look at the yellow blocks. Do you see the yellow blocks here? Look at these yellow blocks carefully. These are the only places, only blocks where both A and B are high, right? Do you see it carefully? See, these are the only blocks where A and B both are high. So that means these are the only blocks where X will be high, right? Everywhere else, X will be 0 because that's exactly how the AND gate operates, right? So this is our second basic gate. I actually tried to add an example, but I'm not focusing on example at this point because we're just learning about the gates. Okay? Now, this is our third and the last basic gate, which is called OR gate. The OR gate gives you a high when any of the input is high. Make sure you see and recognize the difference of the symbols because every symbol is unique and different. Do you see it's a little bit different, right? Because this is band, right? See, look at the symbols and they are different because at some point we'll have only the symbols in the circuit. Just like the electric circuit, right? What happens in the electric circuit? You have like different symbols. Symbol for the battery, symbol for the source, symbol for the resistance, symbol for ammeter, symbol for voltmeter, symbol for switches, right? Similarly, we have symbols for like gates, right? So we have to identify what gate is, which symbol means what gate, right? So that we exactly know what gate will behave like what on which logic. Okay, again, this is an OR gate. It gives you high when any of the input is high. So we have a truth table here. So 0, 0. So none of the input is high, right? So the output will be 0. 0, 1. See, one of the input is high, right? So output will be high. Again, 1, 0. One of the input is high, so output will be high. 1, 1. Both of the inputs are high, so of course it will be high, right? So this is exactly the gate is defined. And just like any other gate, we have an expression for this gate which is x equals to a plus b. X is the output, a and b are the input, and this plus is called binary addition and also called Boolean OR gate because this is actually an OR gate. Now, even if this looks like an addition, but remember this is a Boolean addition, right, or binary addition. Anything which has two different choices like zeros and 1 is also called Boolean. Okay, so but what is the difference between this plus and the regular math plus? Here is the difference. This plus actually works just like the truth table you have, because when a equals to 1 and b equals to 1, what will be the x? 1, right? So that actually means 1 plus 1 equals to 1, because this is a logical 1. This is not like 1 in the math class, right? Because in the math 1 plus 1 is 2, right? But in our case 1 plus 1 is 1 because this one is a logical 1. Okay, and this plus means the OR gate, and it will exactly tell how we have our truth table, right? Because 1 and 1 plus OR give you a high, right? So that's why when A is 1, B is 1, 1 plus 1 is 1 in X, right? Again, I randomly picked two waveforms, and I just want to make sure you see that how, when the X will be high and low based on these waveforms. So look at these yellow blocks carefully. So if you look at the yellow blocks, these in these blocks, either X, either A or B or both are high, right? Check the yellow block carefully. In all the yellow blocks, either A is high or B is high or both are high. So that means these are the places where your X will be high, right? That's exactly how the OR gate is defined. So this is actually our last basic gate, but we'll look at some more additional gates. Okay. Now those gates are not basic gates, but we still talk about those gates because we still use those gates to sometime to simplify our circuit to make it small. Okay. But even if you just know these three gates like AND gate, OR gate, and inverter, you can build every single digital circuit of the world, even the circuit you have inside the computer. But it will be a very, very big circuit. But it will be same circuit. That's what I'm saying. But you cannot probably make it so compact. It will be bigger. Okay, this is our first non-basic gate. This is called NAND gate. Okay. Now this symbol is pretty close to AND gate, except this bubble. Remember, there was no bubble in the AND gate. Okay. Now this gate produces a low output when all inputs are high. That means every other time output is high. So for an example, the first time in the truth table it is high, second time is high, third time is high. Only when all the inputs are high, you see here at the last row, all the inputs are high, right? The output will be low, right? That's what we have here. So again, just like any other the logic gate, we have an expression. The expression is A and B is ANDed and there is a bar on top of it, right? But as I said, we cannot write the bar in many places, so that's why we use prime. And since the bar is on top of A and B both, to explain it, what we do is we put a parenthesis and then put a prime. That actually means that prime is actually applied on both A and B. See, we put a parenthesis, right? And then we put the prime. That means that the bar is on top of the whole thing. But in pause we'll be just writing the primes. Again, I picked two waveforms, and then we'll see where so look at the yellow blocks. Now if you look at the yellow blocks, these are the places where both of the waveforms are high, right? That means these are the places where your output will be low, and everywhere else it will be high, right? See the X? So it's actually the same thing. I'm saying the behavior, the truth table, and the waveform, how it is working is exactly the same thing. And soon you will realize that the expression will also tell you the same thing. So this is our next gate, which is NOR gate. If you look at this symbol of the NOR gate, it's pretty close to OR gate except the bubble at the end. Okay. Now this NOR gate gives you a low if any of the input is high. That means for the first time, none of the input is high, right? See, in the truth table, none of the input is high, so it will give you a high. But every other time, it will give you a low, because either input or both inputs are high, right? So just like any other gate, there is an expression, which is A plus B whole bar. To explain the whole bar using the prime, we use a parenthesis and then put a prime, just to make sure we understand. Anybody understands that the prime is applied on the whole thing. A plus B. So the waveforms, these are the blocks where you see any of the inputs are high, right? See, any one is high or both ones are high. So that means these are the blocks where the output will be low, meaning the X will be low. Next gate is called exclusive OR gate. In short, we write it as XOR gate, but this is called exclusive OR. Okay. Now this symbol is pretty similar to the OR gate, except you see this band curve. We have actually two different curves there, right? The band ones, double. Now this gate gives you high when both of the inputs are opposite. This is really interesting. If both of the inputs are opposite, then it gives you a high. So let's look at the first row. None of the inputs are opposite, right? So it's 0. Second row, inputs are opposite, right? So it gives you high. Third row, inputs are opposite, right? It gives you high. Fourth row, inputs are not opposite, so it gives you 0. Now exclusive OR is a little bit different because this is the expression for the exclusive OR, A prime B plus AB prime. But sometimes we just use this symbol A plus B, but this plus is circle. But in a lot of places you cannot use this symbol, so that's why we actually go by the other way, like A prime B plus AB prime. It still gives you the same expression. Waveforms, we are just highlighting all the blocks. If you look at the blocks, yellow blocks, these are the places where both of the inputs are opposite. Meaning either A is high, B is low, or A is low, B is high. Is that correct? Check the yellow blocks. It's actually all the flip. That means these are the blocks where X will be high, right? To understand the property better, okay? So I try to give you an example at the bottom, but I'm not focusing on the example at that much because at that point we're just focusing on the gates. This is actually the last gate for today, which is called exclusive NOR gate. In short, we write it at X NOR gate. Look at the symbol. This symbol is pretty close to exclusive OR gate, except the bubble at the end. This gate gives you high when both of the inputs are same. So that means at the very beginning both of the inputs are same, right? So it gives you high. Then both of the inputs are not same, 0. Both of the inputs are not same, 0. Both of the inputs are same, so high, right? Now the expression A prime B prime plus A plus B, there is a separate way of writing it, but we don't use it in POS, which is a dot circle, right? We don't use this one. So waveforms, I randomly picked A and B. If you look at the yellow blocks are the one where you have both of the inputs are same, right? Like either both of the inputs are 0 or low, or both of the inputs are high or 1, right? That means these are the places where your X will be high. Now this is pretty much the end of all the gates that we have on our list, but we'll be pretty much using most these gates in the labs. But to understand these gates, I just try to show you how you will actually get this gate. These gates come to you as an IC. Okay? Now, in any IC, for an example, I'm not sure you can recognize at this point because you are just the beginners. So the first gate that we have here, you see here all these gates are like NAND gates. So in one IC, you actually have 4 NAND gates. Do you see it? So in each of the NAND gate, there are 3 pins, right? For an example, for this NAND gate, inputs are 1 and 2. The pin number 1 and pin number 2, output is pin number 3, right? For the next NAND gate, 4 and 5s are input, 6 is the output, right? So pretty much, if you use this IC, you will actually get 4 NAND gates. Now all these IC belong to a family of IC called 74. So basically the numbers you give here, this is 7400. I just wrote the last 2 letters because all these starts with 74. Now the next gate is 7402. You know what I'm saying? This is all, can you identify what gate it is? This is actually the NOR gate, right? I think over the time you probably identify it very better. This is the inverter, right? 7404. So you pretty much will identify all the gates very soon. This is the AND gate, right? 7408. So you don't have to memorize all these gates at this point. These are just as an example. Now I tried to give you a list of quick indexes like key terms, but it's just for your information. But this lecture actually from the chapter 3 of the book, and this has actually 5 quizzes just at the beginning of the quiz section. Okay. Now the idea is you will go over these quizzes as soon as possible, okay? So all the quizzes, just like any other quizzes, you have unlimited number of chances, and you actually have to get 65% in each of these quizzes so that you can try the next one. Okay, so after this point we'll actually keep working on these quizzes and try to finish it by the next class so that we can start something, and then in case you have question, you struggle, we'll answer your question and we'll figure it out. Okay, so I'll stop this presentation here so that we can work on our quizzes.